So in this podcast I want to discuss the trajectory of a projectile. So we're going to consider for concreteness a projectile that starts at the origin at time t is 0 and it is fired upwards at an angle theta from the horizontal with an initial speed v. So the projectile is going to go up like this and it is decelerating upwards due to gravity, and then it will reach maximum height. We want to calculate that, and it will then start to come down, and where it hits the ground is its horizontal range, and we want to calculate that as well. The language I'm going to use to calculate this involves vectors, and I is going to be the unit vector in the horizontal direction and j is the unit vector in the vertical direction. To solve the problem we're going to need boundary conditions, so we're going to need that at t is 0 it starts at the origin, and that also at t is 0 the velocity is v cos theta in the horizontal direction and v sine theta in the vertical direction, and we get that just by looking at this velocity vector in this direction and breaking it into horizontal and vertical components. So, to calculate the problem, we're going to use a little bit of mechanics, and I'm going to look at that on the next slide. So, to solve the problem, we're going to start off by recognizing that the acceleration on Earth for a projectile is constant. It is vertical and downwards, and its magnitude is little g, which is the acceleration due to gravity. And we also recognize that acceleration is the rate of change of velocity, the velocity vector here, with respect to time. So acceleration is the derivative of velocity with respect to time. And that tells us immediately that velocity is the integral with respect to time of acceleration. And we are going to need to add on an integration constant because this is an indefinite integral, and I'm going to call the integration constant c sub 1. And the integration constant is of course a vector. This is a vector, so we integrate the vector here and we add to it an unknown vector. So let's carry out the integral. We see that the velocity is the integral of minus gj dt plus a constant, and the integration is very simple because little j here is just a fixed unit vector. It does not depend on time. G is a constant, here's a minus sign, so we just obtain from the integral minus gt in the j direction plus an integration constant. So now let's recall one of our boundary conditions from the first slide, and that was that at t is 0 the velocity was v cos theta in the I direction, that's the horizontal part, plus v sine theta in the j direction, that was the initial vertical component of the velocity. So now if we compare this and this expression and we put t is 0 in, we see at t is 0 this term vanishes and we are left with c1. So this tells us that c1 is equal to this. So we can just say immediately that this is equal to our integration constant. So from this we see the velocity, I'll be very explicit, this is a function of time, is equal to, and I'm going to write the horizontal part first, so this is v cos theta in the I direction, and then in the j direction we have two terms, so we have v sine theta from our integration constant, and then we also have minus gt in the j direction, so that's minus gt in the j direction. And now if we look at this, I think this is fairly easy to understand. The horizontal component is constant. In our work here we are ignoring air resistance, and the horizontal component of the velocity as the particle follows its trajectory is unchanged. The vertical component at t is naught. We get rid of this. It starts with v sine theta, so it has a vertical component going up, and this becomes smaller with time until eventually it hits the ground. So our next question is to work out the trajectory, the position vector, as a function of time, and in the same way that we obtained v by integrating a with respect to time, we can obtain r by integrating v with respect to time. So let's just summarize that. So we now recall that v is the derivative with respect to time of the position vector. So the velocity is the rate of change of the position vector with respect to time. So this tells us that r is going to be the integral of v with respect to time, plus of course an integration constant which I'm going to call c2, and it is of course a vector. So therefore we obtain that r as a function of time is the integral of v cos theta I plus brackets v sine theta minus gt j with respect to time plus c2. So again, this is a constant, this is a constant, and this is just t times constants, so the integration is straightforward, and we obtain r as a function of time is v cos theta times t I plus v sine theta times t minus a half gt squared, all in the j, the vertical direction, plus c2. So just to make it clear that t is not in the argument of the trigonometric function here or here, I'm just going to put some brackets around the angles. Now let's recall our boundary condition. So at t is naught, r of t is 0. So this tells us, if we put t as naught, well this vanishes, and this vanishes. So since this has got to be the 0 vector, it tells us that our integration constant c2 is itself 0. So therefore we obtain our result. So we see that r of t, this is the position vector that describes the trajectory, is v cos of theta t I plus v sine theta t minus a half g t squared j. And this is our answer for the position vector. So now what I want to do on the next slide is to use this formula that we've obtained to obtain the maximum height and the position vector and the range of our trajectory, and then on the final slide I will just try to understand the formulae that we're going to obtain. So let's move on with this equation here to the next slide. So on the previous slide we obtained the result for the trajectory vector, the position vector given here, and we also obtained the formula for the velocity vector written here. And of course, once you have the position vector, you can obtain the velocity vector by differentiating this with respect to time, and that's a simple check that we haven't done anything too obviously stupid. So we want now to use this to find the maximum height of our particle that's being fired along this trajectory, and also the range. So what is the maximum height? The maximum height is the position, or the vertical part of the position, when the velocity is horizontal. So the horizontal component of the velocity is constant, we've seen that earlier. This is the vertical part, so at the maximum height this is going to be 0. It's where it's going up, getting slower and slower. Its vertical component is suddenly here 0 for a moment, and then it becomes negative, and it goes down faster and faster until it hits the ground. So at the maximum height, v sine theta minus gt is equal to 0, so t is v over g sine theta. So this is the time at which the particle has achieved its maximum height, and now we substitute this time into the vertical part of the position, and that tells us what this height is. So at this time, the height is, so it is v sine of theta times t, and this is the value of t, so it is v over g sine theta minus a half g, and now it's t squared, and t is given by this, so it is v over g sine of theta, just trying to squeeze this in here, all squared. So this tells us that the maximum height is, just tidying this up a little bit, so we have v times v over g, that's v squared over g, times sine is sine squared theta, and then here when we tidy this up we have v squared over g squared, but there's a g here, so that's going to give us v squared over g again, exactly the same, v squared over g, and then there's a sine squared again, just as we had here, and this comes with minus a half. So these two terms are essentially the same, but this is one of this factor, minus a half, so we're left overall with plus a half, so it is a half v squared over g sine squared theta. So that is the maximum height achieved by the particle. And we can think a little bit about that in a moment and see if we understand it, and I'm going to do that on the next slide, but let's look now at the range. So how far does our particle get before it hits the ground again? So the range is when the vertical component of the position is 0, so when it comes down and hits the ground again. So we want this to be 0. So the height of the particle is 0, is the time that tells us what the range is going to be. So we solve this for the time, substitute it back into here, and that gives us the distance at which it hits the ground. So the particle is going to hit the ground, so ground is hit when v sine theta t minus a half g t squared is equal to 0. So that's when this height vanishes. So it starts at 0, it goes up to the maximum height, comes down, and then the vertical component vanishes again. So here we have a quadratic, and what I'm going to do is factorize it. So this tells us that we have t times v sine of theta minus a half gt is equal to 0. So therefore we have two solutions, and the solutions are t is 0 in seconds presumably, and that's not the solution we're looking for because that corresponds to when it was fired from the origin at t is 0. So that's not interesting. And the other solution is when v sine theta is equal to a half gt. So if v sine theta is a half gt, 2v sine theta is gt, so 2v over g sine theta is t. So we can just write that straight down. So t is equal to 2v sine of theta all over g. And that is the solution that we are interested in. So this is a non-zero time when the particle hits the ground again. So we take this time, we substitute it into the horizontal position, and that tells us what our range is. So therefore the range is going to be v cos theta times t, and this is t, so it's times 2v over g sine of theta. So this we can now tidy up, and so we have got v times v is v squared over g, just like here, and then we have 2 cos theta sine theta, and I can write that using a double angle formula as the sine of 2 theta. So the sine of 2 theta is 2 sine theta times cos theta, so I can simplify this and not write it out in such gory detail by using the double angle formula. So this is equal to v squared over g times the sine of 2 theta. And that is our answer for the range. So on this slide we've used our solution for the position vector of our trajectory and the velocity vector that our particle follows, and we've worked out what the maximum height was by identifying the maximum height as being given by the time when this component of the velocity is 0, and we've worked out the range, what this distance is, by identifying that as corresponding to the time when the vertical component of the position vanishes, and we substitute that time into here to find the range. So these are our answers, and on the next slide I just want to describe why we have this factor of v squared over g in both cases, and also to discuss if we can understand anything more about why we might have these factors. So with that we'll go on to the next slide. So on the previous slides we've obtained the following formula for the height of the particle on its trajectory, and I'm going to call the height now capital H, and this formula was the formula for the range that we obtained, and I'm going to call the range capital R. And on this slide I'm going to view little g, the acceleration due to gravity, is fixed, and v as the initial speed as fixed. And what I'm going to be considering is how these two quantities depend on the angle that you fire it. So let's look first of all at the maximum height. If I fire it at an angle of 0, so I fire it horizontally, the height is going to be 0. If I fire it straight upwards, so theta is pi over 2 or 90 degrees, I'm going to get the maximum height I can get because all of the energy is dedicated to firing it upwards as high as it can go. So I'm expecting extreme values when theta is 0, that's the smallest possible height, and theta is pi over 2, that's the maximum possible height. So let's just see if we get that from considering this. So the derivative of h with respect to theta is going to be, so we have a half v squared over g, that's constants. Sine squared theta, we'll pull a 2 in front, reduce the power by 1, so that will go to sine of theta. Multiply them by the derivative of sine of theta. So we're going to get a half v squared over g times 2 sine theta d by d theta of sine of theta, which is going to be the cosine of theta. So the 2's will cancel and we get v squared over g sine of theta cos of theta. So the extreme values are when the derivative vanishes, and the derivative will vanish when sine of theta is 0, which corresponds to theta is 0, and when cos of theta is 0, which corresponds as expected to theta being pi over 2, firing it straight upwards. So the extreme values, the extrema of h, are at theta is 0 and theta is pi over 2, which corresponds to 90 degrees. So that makes perfect sense, and it gives us a better understanding of this factor here. It gives us some confidence that it's correct as well. What now about the range? So we look at this, and in the same way we want to differentiate it. Let's think what we expect. If the angle is 0, it never takes up off the ground, so the range is going to be 0. If the angle is pi over 2, we would also expect the range to be 0. It goes straight up and down again. So somewhere in the middle between 0 and pi over 2, we would expect there to be a maximal range, so a maximal horizontal distance covered. So pi over 4 is what we would expect by symmetry. So in the same way, the derivative of the range with respect to theta is v squared over g, which is a constant as far as theta is concerned. The derivative of sine is the cosine of 2 theta times the derivative of 2 theta with respect to theta, which gives us a 2. So I can just put the 2 in front and we get the cosine of 2 theta. So this vanishes, so the extremum is at 2 theta is pi over 2, so theta is pi over 4, and in degrees that is 45 degrees. So again, that makes sense. It is what we would expect. Pi over 4 is the angle that you launch it at, which you would expect to get a maximum range. So again, this gives us some confidence and understanding of this factor. So to finish the podcast, what I want to understand now is why we have factors of v squared over g. So finally, why v squared over g factors? And the key thing to recognize is that both r and h are distances. So r and h are distances. So in terms of units, they must be measured in meters, but in terms of dimensions, they are going to have dimensions of length. So the dimensions of length. So let's look at the dimension of h, for example. It is the dimension of a half v squared over g sine squared theta. Now, a half is just a number, and sine of theta is a trigonometric function, and that just depends upon angles and is dimensionless. So this has no dimension and this has no dimension. So the dimensions of h are actually just the dimensions of v squared over g. So it is the dimension of v itself squared over the dimension of g. And v is a velocity or speed, so it has dimension of lt to the minus 1, and little g is an acceleration, it has dimensions of lt to the minus 2. So the dimensions of h are lt to the minus 1, and then we square it, it's v squared, divided by the dimensions of g, so it's over lt to the minus 2. So when we expand here in the numerator, when we square it, we're going to get L squared from squaring L, and t to the minus 1 squared is over t to the minus 2 over LT to the minus 2. So this and this cancel, and L squared over L is therefore going to have dimensions of L. It is a length. And in exactly the same way, because it is the same factor in terms of the dimensionful quantities, this is again just a number, we have v squared over g here, it also has dimensions of length. So that explains why we have this common factor. It is a length, and it sets the scale for how high the particle will go and how far the particle will travel. But of course there are geometric numbers, and there is a dependence on a dimensionless angle in both cases. So I hope that's helped you better understand these two results, and with that I'll stop the podcast.